have all these processes enhanced. Compared to these, there are also other processes which are independent of any angle parameter, like Z couples to two charged Higgs bosons, photon couples to two charged Higgs bosons, etc., like this. I took this from Haber's paper, 1997 review. I'm always citing what paper is used. You can see it out there. Okay. This is important for phenomenology. Let's look at one thing. There are certain parameters, forget about them, this maximum and minimum. I put tangent beta equals 3, the scaling Higgs boson is 1 TeV, mu parameter is minus 200 GeV. I skipped mu parameter because I wanted to skip superpotential. That's why I was in that way. And you see that for small or large mixing, it doesn't matter, but the Higgs boson mass starts from a certain value at when supersymmetric breaking scale is here, let's say at 500 GeV, it starts at some value and grows and remains almost constant. Let's change tangent beta to 30. You see that same mass remains again in this way, in a flattened way. This is important. In supersymmetric theories, for Higgs boson mass to agree with the data, you have to include radiative corrections. But even if you include radiative corrections, it doesn't matter. Higgs boson mass never exceeds 130 GeV. Higgs boson mass has to be below 130 GeV. In supersymmetry, we have an upper bound of the Higgs boson mass. It's a built-in property of such models. Okay. Of course, if you extend the supersymmetry model to include more strings, blah blah, then you can change this bound. You can relax it. But in minimal supersymmetric standard model, Higgs boson has an upper bound. It's not a lower bound, upper bound. So if this model is true, Higgs boson mass should be smaller than 130 GeV. 130 GeV. Okay. According to lab experiments, what is the situation? By the way, I'm continuing. Let me finish, just finish, then we will get through it. No, let me finish, if you like. Okay, this is the bounds from lab experiments, okay? Lab has searched for Higgs boson over years, okay? They have collected a huge amount of data. When they analyzed this data and they plotted this possible lattice Higgs boson mass against tangent beta here. Tangent beta is the fundamental parameter of the theory. Okay? We don't know what it is. There are certain regions which are inaccessible. For instance, this region is theoretically inaccessible. This region is excluded by that. This region, this other region has tension with electroweak symmetry breaking probably. It's not written here. Oh, we are left only with the white region. Okay? White region. So, if tangent beta equals 10, then I am allowed to be in this region. But for instance, if tangent beta equals 1, there is no way. Tangent beta, this parameter should be greater than 3 or something here. But there is a small region here, again, allowed. We should not forget it. And it corresponds to very small tangent beta. Okay? The white regions are the ones allowed by the experiment or theory. So we are searching for Higgs boson and supersymmetry, and this is the region, or this is the region allowed by the data. Let's continue. Let's continue the Higgs production. Just as I did yesterday, I will show you production of these Higgs bosons in colliders. So I will first start with Tevatron, which is not a healthy collider at all, but let's see. Let's see the predictions. This analysis is done for Tevatron with a central mass energy of 2 TeV, etc., etc. Tangent beta equals 30. No, I say tangent beta equals 30. You see the reason here. Lattice Higgs boson is never heavier than 130 GeV. Therefore, lattice Higgs boson graph will always end at 130 GeV. And then I start heavier Higgs boson graph right at that scale to be in the right scale. So there is nothing wrong in this graph. This graph is correct. The thing is that this side belongs to lattice Higgs boson, this side belongs to heavier CP even Higgs boson. Yeah, as you see, Higgs boson, the dV1 has the largest ratio here, as you see. Gluon to Higgs also competes with the BB bar process at this scale around when Higgs boson is around 80 GeV or something. And when Higgs boson arrives around 200, when heavy LCD, even Higgs boson is around 200 GeV, we know that Higgs to BB bar and Higgs to gluon just compete with each other. They are close to each other, what I mean. This is the situation. This is not in the standard model, because in the standard model, Higgs boson masses are arbitrary thing. You can vary this quantity the way you like. But here you have an upper bound. You cannot go further. You have to finish your graph somewhere. This is the scalar Higgs boson. You see, this is the generation of the scalar Higgs via BB bar process. This is via gluon process. This is again gluon and QQ bar with the production of BB bar and scalar Higgs. They have all these sizes. This is again picobarn, 10 to 2, 100 picobarn. Here again, cross section. Here, charged Higgs production. BB bar, you produce a charged Higgs boson in picobarn. It is something around 1 picobarn level, when tangent beta equals 50, and 2 and 10. And here is the charged Higgs boson mass. Actually, this graph is not realistic at all. Charged Higgs boson and the scalar Higgs boson will be presumably heavy, 2 to 400 GeV. No one cares. But in any case, this is the case that you will see schematically. At the LHC, let's see what will happen at the Large Hadron Collider. At the Large Hadron Collider, of course, collider is huge. We expect something crazy. In picobarns again, we expect that cross-section is around 1000 picobarn level, which means it's nanobarn, okay? Nanobarn level cross-section. When the Higgs boson mass is around here, at this level, 100 GeV level. As you see, like Higgs boson graph will end around 130 GeV, so it is this part belongs to light 6. Heavier Higgs boson has this size, and as you see, at the LHC, BB bar production somewhat dominates the other processes in a, let's say, in a magnified way. And here you see the contribution from standard model Higgs boson. Gluon fusion into Higgs boson contribution is this. You see, in supersymmetric part we have this region and this region, but in standard model prediction is this. Which means that for light Higgs bosons around, let's say, 100 GeV or something, the supersymmetric contributions are larger than the standard model expectations, of course, for these parameter ranges. And again, for LHC, which is a scalar Higgs production, it is of this type, and there is this BB bar and gluon fusion, and here is the standard model contribution. Here is charged Higgs boson. It runs from 10 to minus 3 to 10 to 100 GeV, again 50 to 30. This graph is more realistic because charged Higgs mass goes up to 1 TeV. This is good because it's nice. It is something expected from the model by the workers of that model, let's say. Here is, you see that cross-section is around 100 picobarns, and which is good. That's telling us that the cross-section is huge. There will be a huge particle production. Finally, let me show you detector simulations. This is the simulation of Higgs boson decays and production, blah blah, for ATAS detector at LHC. With an integrated luminosity of 300 femtobarn inverse, and for each mode is shown by a different color. Let me try to tell you what's going on. For instance, Higgs to gamma gamma, W Higgs, TD bar Higgs, Higgs to gamma gamma, etc. is this bound. For instance, Higgs, heavy Higgs decays into two light Higgs bosons decay into a BB bar and a photon has this signal, and when tangent beta is around 4. At large tangent beta, we don't have a strict bound, but this graph, this contribution, TT, H, and Higgs to BB bar contribution, this is something special to large tangent beta domain. For smaller tangent beta domains, we have these kind of processes. And this is the situation, this is the expectation at the Atlas detector in LHC. Here we have pseudoscalar Higgs mass, here we have tangent beta, fundamental parameters of the theory. Of course, from this geographical distribution of the decays and production decay rates, we are able to say, I don't know, I mean, if one measures something here, then one can perhaps say, or make a prediction about other things around. And let me show you the simulation in the CMS detector at LHC. This simulation is at 30 femtobar inverse, which is much smaller than the other one. Maximal stop mixing, etc., etc. Here again, pseudoscalar Higgs mass, here again, tangent beta. As you see, each mode contributes in a different range of parameter range. For instance, this is for heavy CT Higgs boson and pseudoscalar Higgs boson to decay into tau electron pair. This is for top quark and charged Higgs boson pair. This is for lepton, etc. Here is Higgs to gamma gamma. You see, when pseudoscalar Higgs boson is around 300 GeV, we expect this Higgs to gamma gamma to be strict. It is important. It is like here, okay, Higgs to gamma gamma. You see, they say 200 GeV, but this is Atlas simulation with a different luminosity or different parameters. Here it is at around, again, 200 to 300 GeV. We expect such a line. That's it. And thank you.
Question. Of course, sure. This is a beautiful thing that you described. In a sense, among other things that come out of the mechanism, there's an upper bound of Higgs mass which sort of eases life a little bit, right?
Yeah.
Well, is there a trade-off with tangent beta in the ratio of the expectation values of the Tubitan complex? Let's see play so wildly along.
Right.
It
is important, yes, that's true. You are right. For instance, let's see this graph. Yes, this thing. Tangent beta normally, I mean, you have a coupling, sir. Top part you have a coupling, bottom part you have a coupling. These are unknown numbers. Suppose we take top part you have a coupling equal to bottom part you have a coupling. They are equal. Then the way to explain top quark and bottom quark mass goes by choosing tangent beta appropriately. You have to choose two vacuum expectation values in a let's say in a well separated way. But experiment is telling us that this is experimental bound. Tangent beta is something around 3 and above. I mean, if precision increases, proportionally the distribution will be closed, and they expect that tangent beta will be pushed to higher values.
What I'm concerned is that there will be eventually, in the context of this particular model, a way of constraining the value of the beta, so that there will be any redundancies at the end of the day.
I see. As far as I know, I don't know. I mean, no one also knows how to measure these parameters. These are all indirect measurements or indirect conclusions, because in collider what you do is to just measure the scattering rate. But tangent beta, it would be nice to constrain this. But no one knows, because of course, given naturalness, you cannot choose one vacuum expectation value to be 100 times the other one. This is crazy, because this means that there is a huge fine-tuning in the associated Higgs sector, because certain mass parameters must be fine-tuned so as to produce this hierarchy between the vacuum expectation values. This is not good, actually. It's neither good nor acceptable. However, I don't know. People are working on large tangent beta. I also worked on large tangent beta domain. Then I didn't like it, because, for instance, in models with an extra U1, Z prime bosons we worked in the past together, their tangent beta is naturally 1. The model doesn't accept other values of tangent beta. And it is able to explain all the existing data with tangent beta equals 1. So two vacuum expectation values are equal to each other already. because Yukawa sector is unknown, and the hierarchy between top Yukawa coupling and bottom Yukawa coupling comes from flavor breaking. I mean, there should be some flavor symmetry somewhere up there, and it should be broken, you should produce all these listings and hierarchy, blah blah. I don't know how to generate it, but working expectation values should be close to each other, to my view.
Any other questions?
I have a question about describing the Suzy theory. I wonder what is the logic of the choosing different two Higgs doublets, different.
Çok güzel. Nice. Higgs doublet. Okay, in supersymmetry the problem is the following. In standard model, for instance, I can write this topic, Q bar Higgs, let's say TR, plus Q bar, let's say Higgs charge conjugate BR. This generates bottom coordinates, this generates top coordinates. Okay? I'm sorry, I forgot Yukawa coupling. They don't have to be equal to each other. But Yukawa Lagrangian is nothing but the superpotential of the theory. I skipped the superpotential to make life easier. Otherwise, it would be confusing. Anyway, let me try to generalize this thing to a supersymmetric framework. I will take top quark and I will make up a top quark superfield. I have to use superfields everywhere. HD, this will be top quark superfield. It will be dotted with a Higgs superfield. Then there will be top quark superfield. Let's come HB, top quark superfield. It will be SU2. This is SU2 Orange asymmetric combination. This don't mean that. And HC superfield PR. The problem is the following. In supersymmetric theories, dagger is not allowed. Okay, that's the problem. I mean, how to say? For instance, Higgs superfield times Q. This superfield is a chiral superfield again. Superfield. But Higgs superfield dagger times spark superfield is not a chiral superfield. Okay, it's a kinetic term actually. Okay, this is not chiral superfield. Not. So what we have to do is that charge conjugation of Higgs double means it involves Higgs dagger. It is there. And instead of that, therefore, in the theory, we should not. The way to accommodate the situation is that there is Higgs here. There should be another Higgs. This Higgs cannot be the same Higgs here. Okay, I cannot have the dagger or the other quantity. But if I don't take dagger, I cannot match the quantum numbers. So I have to use, let's say, this is HU, this is HD. Some two Higgs doublets. Then I can use HU and HD. This is a new Higgs doublet. This is somehow enforced on the system. Also, there are other arguments coming from leptonic sector. If you use the same single Higgs doublet, you can identify lepton doublet with the Higgs doublet. In standard model, they don't have a difference. They have the same quantum number. Okay, but in supersymmetry, there is a difference between them. That is the R parity, etc. Okay, so there is a difference between the leptonic and Higgs sectors only in supersymmetry, not in standard model. In standard model language. What I mean is that lepton doublet is nu and L, nu and E, and HU. What was it, phi plus, phi 0, something like. They have the same quantum numbers in standard model. Okay, they have the same quantum numbers. And it is only in supersymmetry that you can distinguish between these two. It's still the alphabet language. That's why we write LHU N as the right-handed material coupling is written in this way, because this is a standard model singlet, so that this new singlet can be imported into the system.
Another question?
As I saw in standard model case, the maximum cross-section belongs to the ground refraction to produce the Higgs. But in supersymmetric case, I saw that it belongs to the BE, which is the maximum cross-section.
Yes.
But I want to ask is, what happened only for B to increase to such
Very good. Very good. It was Professor Park's question actually. I am choosing tangent beta to be 30. Okay? Because Yukawa coupling of Higgs boson to B bar involves equal Yukawa coupling HB times in standard model language times tangent beta. Since I choose tangent beta 30, this is 1 order of magnitude larger than standard model coupling. Because of that, I have a competition between BB bar process and gluon process. If I were choosing tangent beta 1, then the result here would be almost identical to standard model expectation. It is tangent beta. I was showing you tangent beta equals 30 grams.
Any other questions? Well, I have one. When you were discussing the stabilization of the Higgs mass, you said that to stabilize it you need a fermion loop.
Yes.
Well, the fermion loop already exists in the standard model, but just you need the fine-tuning between the Yukawa couplings. If you can live with that Yukawa coupling, do you still have any problems left, or is all your problems?
Let's look at the counting, and let's look at if we can cancel all of them. So let's take bosonic loops. Higgs self loop, W boson contribution, Z boson contribution. These are the bosonic loops. Okay. Then let's start having fermion loops. Fermions. Let's include them, and the largest contribution will come from top part. This was done at the beginning of 1980s. Okay. People tried in this way, and even they wrote many papers on this to cancel this divergence. It didn't work finally. Okay. Because tuning in the Yukawa couplings is not consistent. Because from the bosonic sector you have a different contribution. From the fermionic sector you have each fermion giving its own contribution. There isn't any unique and sensible solution in that sense. That's
Natural. It's not natural, right?
It's not natural.
You force it.
Yeah, even if you force it, of course, Arthur's point is important. Maybe we would solve for Yukawa couplings in that case, but I mean, there should be a symmetry reason for this. There should be a symmetry reason, I think.
Any other questions? So let's thank the speaker.